welcome to the Deep Dive. If you're tuning in today, you are likely navigating the thick of Dave Reed's CS330 class.
Yeah, programming languages and compilers over at Skidmore.
Exactly.
Yeah.
And we've got a really solid stack of material today. We're focusing squarely on the presentation notes from Class 14.
Right, the one on data types.
Yeah, but we're also keeping one eye on the syllabus just to contextualize the rather intense workload you have coming up this week.
It is definitely a heady week.
It really is. So our mission today is to sort of unpack the hidden architecture of the digital world. I mean, we use and write software constantly, but rarely do we pause to analyze how a programming language actually manages the fundamental building blocks of information.
Down at the hardware and compiler level, you mean?
Right. Like, how does a computer actually enforce the boundaries between a character, a Boolean, and an integer?
It's a fundamental question, and to guide us, we really need to look past the surface-level syntax.
Yeah.
I mean, why does it actually matter how a programming language defines a simple string of text or a numerical value?
Well, it seems basic.
It does, but if we connect this to the bigger picture, it turns out that the way a language handles data types determines practically everything about your software's behavior.
Everything.
Yeah, it dictates how fast a compiled program executes, how efficiently memory is utilized on the heap or the stack.
And crucially, whether your code base is going to be riddled with invisible, completely silent logic errors.
Exactly. Those are the worst kind.
Okay, so let's unpack this, because it is incredibly easy to think of a data type as just a label.
Like a sticky note.
Right. A label you just slap onto a variable declaration, like this variable is an integer or that variable is a string.
Yeah, that's how it's often taught initially.
But looking through Dave's material, that is just scratching the surface. A data type actually consists of exactly two mathematically rigid concepts.
Which are the specific collection of allowed values.
Yep, combined with a strictly defined set of predefined operations.
Exactly. When you declare a variable in any strongly typed language, you aren't just giving the compiler a friendly hint. You are implicitly defining exactly what can and cannot be done to that memory address.
So if you define something as a Boolean.
Right. The allowed values are strictly true or false, and the allowed operations are logical constructs, like A and D or R and not T.
You simply cannot multiply two Booleans together.
The compiler physically prevents it. And what's fascinating here is why language designers are so draconian about this enforcement.
Well, it boils down to three core architectural pillars, right?
Yeah. Early error detection, enforcing modularization, and establishing self-documenting code.
Okay, let's talk about the error detection piece. If the compiler knows the exact mathematical boundaries of a variable, it can catch a type mismatch during the compilation phase.
Long before the program ever hits a production environment.
Which is a lifesaver. But here's where it gets really interesting to me. The underlying mechanism for all of this is something called a descriptor.
Descriptors are brilliant.
Right. Instead of a basic tag, think of a descriptor as this complex metadata payload that the compiler or interpreter attaches to your variables.
It's an attribute completely separate from the variable's identifier. It's doing all this secret bookkeeping in the background.
Secret bookkeeping is the perfect way to conceptualize it.
Yeah, and the compiler maintains this metadata payload either at compile time, when it's translating source code into machine instructions, or at runtime if you're using a dynamic language.
And this descriptor tracks vital system attributes.
Exactly. It holds the type name, the exact address in memory where the data block begins, and the specific length or size of that data allocation.
So the language is essentially using this metadata payload to enforce the rules of the road.
Precisely. The compiler utilizes these descriptors for strict type checking. If you attempt an illegal operation...
Like adding a string literal to a floating point number.
Right. The compiler cross-references the descriptors, recognizes the mismatch in the predefined operations, and just halts the build with an error.
It also relies heavily on this information for the allocation and deallocation of memory.
It only provisions the exact number of bytes necessary to store the value based on the type definition. It's the invisible infrastructure keeping your execution environment stable.
So what does this all mean when we get down to the bare metal? Let's look at primitive data types.
The foundational stuff.
Yeah, because these primitive types are not built out of any other composite data types. They map directly and incredibly efficiently to the computer's underlying hardware architecture.
We're talking about numeric types like integers and floating points, booleans and characters.
Yes, and because they map so intimately to the processor's architecture, they execute with massive efficiency.
Your processor literally has dedicated arithmetic logic units designed specifically to crunch standard integers.
And common byte allocations for integers are usually what? 1, 2, 4, 8 bytes.
Typically, yeah. But this raises an important question regarding signed versus unsigned numbers.
Oh, this part is great.
It requires a brilliant, albeit restrictive, hardware compromise. The notes call it the 2's complement.
I really appreciate how the class notes break down the math on the 2's complement. Systems use this hardware design to simplify arithmetic operations with signed integers.
Meaning numbers that have to cross the zero threshold into negative territory.
Right. But the compromise is that you have to sacrifice the most significant bit just to represent that positive or negative state.
It is a fundamental trade-off of hardware design. In a standard chunk of memory allocated for an integer, all the bits are typically used to represent the magnitude of the value.
But if your software logic requires negative numbers,
that first bit becomes the sign flag. So if we take an 8-bit integer, it normally holds 256 distinct discrete values.
if it's explicitly defined as unsigned, the mathematical range goes from exactly 0 to 255.
Exactly. But the moment you apply 2's complement to make it signed, that entire numerical range shifts downward.
It becomes negative 128 to positive 127.
You permanently lose half your positive computational range just for the privilege of representing values below 0.
Though it is worth noting that for specific use cases where that byte limit is a huge bottleneck, some languages offer arbitrary precision integer types.
Right, which use proprietary internal representations to allow for massive numbers.
It frees you from strict byte limits, albeit with a noticeable performance hit.
Yeah, since it no longer maps directly to a single hardware instruction.
And it's not just numerical arithmetic that maps to the hardware. To a processor, a letter of the alphabet doesn't actually exist.
No, not at all. Characters are strictly stored as numeric mappings.
And there is a massive amount of computing history embedded in those specific numeric mappings.
ASCII is the big one. The American Standard Code for Information Interchange became the dominant standard across the industry.
But fascinatingly, early ASCII was strictly a 7-bit code format.
Which always throws people off.
Yeah, because we are so accustomed to the 8-bit byte being the standard computing quantum.
The 8th bit of the byte in early character encoding was historically just reserved for parity.
Right, a very primitive form of hardware error checking for data transmission over noisy analog lines.
Exactly. We eventually transitioned to extended ASCII, reclaiming that 8th bit to add 128 additional special characters to the mapping table.
And while ASCII won the broader war, it wasn't the sole standard.
No, IBM created a heavily competing standard called EBCDIC.
EBCDIC.
Yeah, and because enterprise computing moves at a glacial pace, EBCDIC is remarkably still operational today on certain legacy IBM mainframe systems.
That is wild. But moving beyond individual characters, when we string those numeric mappings together, we arrive at the string data type.
Which introduces a massive design dilemma for language architects.
Strings are the universal plaintext medium of the digital world. If you want to exchange data between entirely different tech stacks or operating systems, you almost always default to strings.
Whether you are parsing a CSV file, structuring XML or JSON payloads, or querying a relational database, that data travels as string literals.
It is infinitely simpler to exchange characters than to try and sync complex binary data structures across different machine architectures.
That interoperability is why strings are ubiquitous. But because they are so fundamental, you might assume every programming language manages them identically under the hood.
But they don't.
Not even close. What's fascinating here is that the architectural decisions around string implementation vary wildly.
Are they dynamically sized in memory or statically allocated?
Are they mutable, meaning they can be altered in place, or immutable, meaning they are locked once created?
The specific implementation a language chooses drastically alters how a developer must approach memory management.
The contrast between C and Java here is the perfect case study.
Let's hear it.
In C, strings are technically not even a primitive type. They are treated merely as arrays of characters.
Okay.
They are mutable and they are dynamically sized. But the major quirk is that the memory footprint of the array might actually be larger than the string it contains.
Because C determines the string's length by scanning memory until it hits a hidden null terminator character.
Exactly, which is incredibly fast for the processor, but it places the entire burden of memory safety squarely on the programmer's shoulders.
So C will just blindly read sequential memory blocks until it encounters that null character.
Yeah. If you manipulate a string and accidentally overwrite or forget that null terminator, C doesn't throw a helpful error,
It just keeps reading raw garbage memory.
potentially exposing sensitive data until it triggers a segmentation fault and crashes the program.
Wow. Now, contrast that chaotic freedom with Java's architecture. Java treats strings as a dedicated library object.
They are statically sized and strictly immutable.
Once instantiated, the text in a Java string cannot be changed.
Right. If you try to append a word, Java quietly provisions a brand new string object in memory behind the scenes and abandons the old one to the garbage collector.
It provides massive safety and predictable thread behavior, but can generate significant memory overhead if you're doing heavy string manipulation.
Python takes a similar philosophical route. It categorizes strings as a primitive type, but like Java, enforces static length and immutability.
C++ Vlim, meanwhile, attempts to split the difference. It uses a derived standard library type that is dynamically sized and mutable.
Aiming for C's flexibility with modern, object-oriented safety nets.
You know, when you sit down and initialize a project in a specific programming language, you aren't just adopting its syntax, you are wholesale inheriting that language's philosophical stance on the balance between memory control and developer safety.
Inheriting the philosophy is exactly right, and that philosophy of safety becomes incredibly stark when we analyze enumeration data types.
Or enums.
Right.
The textbook goal in an enum is straightforward: to provide all allowed values as explicit named constants.
It exists to vastly improve the readability and reliability of a code base.
Instead of a developer having to memorize that the integer 1 corresponds to a red state and 2 corresponds to a blue state, you just define the explicit variables red and blue.
The language recognizes them as part of a strict mathematical category called colors.
In a strictly typed language environment like Java, Python, or C#, enums provide immense architectural reliability.
The compiler strictly enforces the operations. You cannot perform arbitrary arithmetic on a color state.
You cannot assign an undefined integer to that enum variable.
The compiler treats the enum as a distinct, isolated type and simply rejects any unintended operational logic. It acts as an unbreakable guardrail.
But that invisible logic error we mentioned earlier perfectly illustrates the danger of loose memory management, especially in C.
Yeah, Dave's notes point out a fascinating and frankly dangerous design choice in C regarding enums.
Behind the scenes, C simply coerces enum values directly into standard integers.
And that coercion is where the type checking completely disintegrates.
Because the C compiler internally maps the enum to a numeric value, it actively allows unintended mathematical operations.
Since red is secretly just the integer 1 in the memory registry, C will happily let you multiply red by blue.
It computes the math and outputs a seemingly valid integer.
But logically, in the context of your application, multiplying two colors is nonsensical.
Because C strips away the type abstraction and treats them strictly as hardware integers, all those reliability benefits vanish.
The compiler is completely trusting the developer to never write a logically flawed operation.
And that danger only multiplies when we start bundling isolated data points together into aggregates.
Moving on to section 5 of the material.
Yeah, let's contrast standard arrays with records and associate arrays. We know standard arrays require homogeneous data.
A sequential list of elements sharing the exact same data type.
But the real friction at the compiler level comes down to range checking and bounds enforcement.
Precisely. For a single-dimension array, the metadata the language must maintain at runtime depends entirely on its bounds checking philosophy.
If the language strictly enforces range checking, meaning it actively throws an exception if you attempt to access the 11th index of a 10-item array,
then those boundaries must be continuously tracked within a runtime descriptor.
However, if it's a statically allocated array in a language like C, there is no runtime descriptor for bounds checking.
C will just let you write data past the end of the array, completely corrupting adjacent memory cells.
Yikes. But standard arrays are rigidly ordered by sequential numeric indexes. Associative arrays, like a Python dictionary or Java's hash map, break that mold.
They do. They are unordered aggregates of data where elements are indexed by custom keys rather than sequential numbers.
Each entry is a pair, a key and its corresponding value. And the data types of the keys and the values are completely independent.
You can map a string key to an integer value,
which fundamentally changes how data is retrieved.
Instead of calculating a memory offset based on a numeric index, the language employs a hashing function.
It takes your custom key, runs it through a mathematical algorithm, and generates a unique memory hash.
This optimizes the lookup process, making data retrieval incredibly fast regardless of the aggregate's total size.
But while associative arrays are powerful for key-value pairs, if you need to strictly define a complex, structured entity containing multiple different data types, you utilize a record.
Right. A record is a heterogeneous collection. It bundles data members of independent types into a single unit.
And the historical context Dave provides here is great. COBOL was actually the first language to introduce an explicit record type back in the 1960s.
It was engineered specifically to define the rigid layout of flat files, like VSAM datasets on IBM mainframes.
Decades before relational database architecture was even conceptualized.
It is a data structure paradigm that has outlasted generations of hardware. Today, in C, records are formally implemented as structs.
Unlike a heterogeneous array where data pointers might be scattered randomly across the heap, the data members inside a C struct sit tightly packed in adjacent memory cells.
You access specific members via precise memory offsets from the base address of the record.
You manage the entire heterogeneous block of memory as a single allocatable unit.
And this ties directly into the critical work the CS330 students are doing right now.
Yes. Dave's material explicitly notes that C structs are the absolute backbone for constructing abstract syntax tree nodes, or AST nodes.
When you are writing a compiler, an AST node representing a mathematical operation needs to store the operator token, maybe a character type, but it also needs to store memory pointers to its left and right child nodes.
A C struct allows you to bundle those entirely different data types into one coherent node entity that the compiler can traverse.
Which is exactly why reading Chapter 6 in the Thing Compiler's book on ASTs by this Friday is non-negotiable.
If you want your compiler project to actually function.
Exactly. The AST structure relies heavily on pointers and structs.
Which brings us to a related and potentially hazardous data type used for aggressive memory optimization.
Unions.
Unions. A union allows a single variable to store one of several completely different data types, but only one at any specific point in execution.
It essentially allows a variable to act as a memory shapeshifter. Yeah, if your program architecture dictates that a specific variable will only ever need to hold an integer or a floating point number, but mathematically never both simultaneously, a union allows them to share the exact same physical memory address space.
It drastically reduces the memory footprint, but the inherent design flaw regarding type checking is massive.
The implementation dictates the danger level. You have discriminated unions, native to languages like Ada or Fshag, which maintain rigorous type checking.
They utilize a hidden tag, essentially a runtime descriptor, to track precisely which data type currently occupies the union's memory block.
But then you have free unions, utilized in C, C++M, and Fortran.
Free unions deploy zero internal type checking.
The language assumes you, the programmer, perfectly remember what type of data you last wrote to that memory address.
Which leads to a brutal logic error outlined in the class notes. And pay attention here because this is directly applicable to Lab 4 on C pointers and memory that is due this Monday, March 2nd.
Okay, set the scene.
If you define a free union in C named number, designed to hold either an integer called num.i or a float called num.f.
Right.
You execute an operation that sets num.i to the integer value 15. The union writes the specific binary sequence representing the integer 15 into that shared memory block.
So far, so good.
But later in the execution path, due to a logic flaw, your code attempts to read the variable as num.f.
And the program does not crash. That is the insidious nature of the error.
Exactly.
A floating point number under the IE 754 standard uses a completely different binary layout for its sign, exponent, and mantissa compared to a standard integer.
But C doesn't care.
It simply grabs the exact binary bits that were formatted for the integer 15 and blindly interprets them through the structural lens of a floating point calculation.
You will not read 15.f.
You will retrieve an absurd, mathematically incorrect value, and the processor will just keep executing, silently poisoning every subsequent calculation in your program.
It is the definition of an invisible bug, which perfectly illustrates why understanding the exact physical layout of C pointers and memory arrays is critical for Monday's lab.
If you don't grasp how C allocates and reads those raw bits, you will be drowning in invisible segmentation faults.
And speaking of course logistics, let's quickly synthesize the rest of your immediate horizon. As we mentioned, Lab 4 is due Monday.
Friday, March 6th, you need Chapter 6 read for AST comprehension.
Also on Friday, the optional extra credit Lab 5 is due. Given that Lab 5 specifically targets C structures and complex memory allocation, I highly recommend tackling it to solidify your grasp on structs before building out your ASTs.
It is essential practical application. And finally, Sunday, March 8th is the deadline for your Week 7 journal entry.
Do not forget Dave's strict 2-1 rule for the journal. Your submission must contain a minimum of 2 substantial paragraphs of reflection and exactly 1 quiz question.
Do not throw away easy points by ignoring the format constraints.
And the reward for surviving this memory management gauntlet. Next week is spring break.
A highly necessary system reboot before you return to parse trees, Lab 6, and the Bison generator.
It is a rigorous academic sprint. But if we synthesize the core architectural themes we have analyzed today, the major takeaway is clear.
Data types are far more than tedious syntax rules enforced by an annoying compiler.
They are the fundamental architectural guardrails deliberately engineered by language designers.
They exist to constantly balance a processor's need for raw, uninhibited computational throughput against the critical necessity of application stability and memory safety.
So, as you head to the computer lab to debug your C pointers, here is a final provocative thought for you to mull over. Throughout this deep dive, we've analyzed data types strictly bound by the binary constraints of classical computing.
Bits that are definitively either a 0 or a 1.
But as we rapidly approach the era of quantum computing, utilizing qubits that exist in a state of superposition, being both 0 and 1 simultaneously.
Oh, that's interesting.
How will language architects even begin to define a primitive data type for a variable that inherently exists in multiple contradictory states at the exact same time?
This raises an incredibly important question about the future of compiler design.
Keep asking those questions, keep digging into the hidden architecture of your code, and we will catch you on the next deep dive.